Alright, in this video we'll be solving the CIE A-Level Maths Probability and Statistics 1, paper 52 for October-November 2024. If you're feeling anxious, overwhelmed, or unsure where to start, then I've created a complete course that streamlines everything with step-by-step videos, interactive quizzes, and an exclusive student community to keep you on track. You can get access to it by clicking the first link in the description. Otherwise, like the video, subscribe, and let's dive right in. Number 1. At a college, the students choose exactly one of tennis, hockey, or netball to play. The table shows the numbers of students in year 1 and year 2 at the college playing each of these sports. One student is chosen at random from the 120 students. Events X and N are defined as follows. X is the student is in year 1 and N is the student plays netball. Part A. Find the probability of X given N. So the formula for conditional probability, if we're dealing with X and N, is going to be the intersection of X and N divided by the probability of N. All right. So probability of X intersection N is the student is in year 1 and plays netball. So year 1 and plays netball is 12. So that's going to be 12 over. Then the probability of N, the probability that they play netball, that's 12 plus 28. So that's 12 plus 28. And so what does this simplify to? This is 12 over 12 plus 28. That gives us 3 over 10. That's our answer. And then part B is now the reverse. So the probability of N given X. So this is going to be again the intersection is in year 1 and plays netball, but now it's the probability of X here. So is in year 1 and plays netball is 12. And then the probability of X student is in year 1 becomes 16 plus 22 plus 12. So that's over 16 plus 22 plus 12. So this is equal to, that's 12 over 16 plus 22 plus 12. That gives us 6 over 25. And then part C says determine whether or not X and N are independent events. So if X and N are independent, then the probability of X intersection N will be equal to the probability of X times the probability of N. What is the probability of X intersection N? So that's the student is in year 1 and plays netball. So we've got 12 students like that. And this is out of a total of how many students? That's 120 students. Okay, and this should be equal to the probability of X, which is the student is in year 1. So 16 plus 22 plus 12. In fact, let's work it out on the side. So that's the probability of X is going to be 16 plus 22 plus 12. And over the total number of students, which is 120. So the probability of X is going to be, let's punch that into the calculator, 16 plus 22 plus 12 over 120. That gives us 5 over 12. So this here should be 5 over 12 multiplied by the probability of N. So probability of N, that's just the student plays netball. That's 12 plus 28. Out of the total number of students, which is 120. So that's the probability of N. This is 12 plus 28 over 120. That gives us a third. All right, so times a third. 12 over 120. What is 12 over 120? 12 over 120 is a tenth. So this is saying that a tenth should be equal to 5 over 12 times a third times a third. That gives us 5 over 36. So this is clearly not equal. So we can say that X and N are not, X and N not independent. Independent. All right. One of the students who plays netball takes 8 shots on goal. On each shot, the probability that she will succeed is 0.15, independently of all other shots. Part D, find the probability that she succeeds on fewer than 3 of these shots. Alright, so let's define our random variable as y. This is number of shots on which she succeeds, number of shots on which she succeeds, on which she succeeds. Okay, so y is going to follow a binomial distribution because we've got a fixed number of trials. Trials are independent of each other. We've got a fixed or constant probability of success, and we only have two outcomes: either she succeeds or she fails. So all conditions for a binomial distribution are satisfied. So that's n is 8 and our probability of success is 0.15. And we want to find the probability that she succeeds on fewer than 3 of these shots. So probability that y is less than 3. So that means we're evaluating 0, 1, and 2. So that's going to be equal to, we'll start with 2. So 8 choose 2 times 0.15 to the 2 times our q, which is going to be 0.85 to the 6 plus 8 choose 1 multiplied by 0.15 multiplied by 0.85 to the 7 plus 0.85 to the 8. Alright, so therefore, the probability that y is less than 3 is equal to, let's punch this into the calculator. This is 8 choose 2 multiplied by 0.15 squared multiplied by 0.85 to the 6 plus, that's 8 choose 1 multiplied by 0.15 times 0.85 to the 7 plus 0.85 to the 8. And this gives us that 0.895, and that's our final answer. Number 2, part A. Find the number of different arrangements of the 9 letters in the word algebraic. Alright, so we've got 9 letters, so it's going to be 9 factorial. And how many are repeated? So A appears twice. So 2 factorial. Is there anything else that appears more than once? I don't think so, no. So it's just 9 factorial over 2 factorial, which gives us, that's 9 factorial over 2 factorial. That's 181,440. And that's our final answer. Part B, find the number of different arrangements of the 9 letters in the word algebraic in which there are no more than 2 letters between the two A's. So this means we can either have 0 letters between the A's. So in other words, we are putting our A's together. And then we'd have 1, 2, 3, 4, 5, 6, 7. That's the rest. So L, G, E, B, R, I, C. Or alternatively, we could have just one letter between the A's. So I'll fix the position of the A's, and then we've got one letter in between, then the other 6 letters, 1, 2, 3, 4, 5, 6. Okay, so this could be L, and then this is G, then this is E, B, oh, B not R, B, R, I, C. Oh, finally, we could have exactly 2 letters in between because they say not more than 2. So 2 is also included. And then we've got 1, 2, 3, 4, 5. So that's going to be L, G, E, B, O, P, R, I, C. Okay. So let's go with the first scenario first. So here we're saying there are no letters in between our two A's. So it essentially means that our A's are going to be together. So the number of arrangements here are going to be 1, 2, 3, 4, 5, 6, 7, 8. So it's just 8 factorial here. So 8 factorial is 40,320. Okay. So this is the scenario where there's 0 letters between our A's. And now let's look at the scenario where there's 1 letter in between our A's. So I want to fix the position of our A's. That way, it means that we can control the number of letters in between our A's. And in this case, we only want to have 1 letter in between. So we're going to be rearranging 1, 2, 3, 4, 5, 6, 7 items. So that's going to be 7 factorial. But notice that I could also shift my A's so that this A is in the position of G, but still maintaining a gap of 1 in my A's. So essentially what this means is that we'd have a gap and then A, and then we've got 1 letter in between our A's, and then the remaining letters 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I could keep pushing my A's to the right, maintaining this gap of 1. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. I could keep doing this until they get to the end, but of course that's tedious, so I'm not going to do it manually. That just means that I can move my A's to this position. So that's the second scenario, that's the third scenario, that's the fourth, that's the fifth, that's the sixth, that's the seventh. So I have to multiply this by 7 because my A's can be in 7 different positions whilst still maintaining that gap of 1 letter in between them. Okay, so we need to evaluate 7 factorial times 7. 7 factorial times 7, that is 35,280. And then finally, we need to evaluate for a gap of 2. So this is 1, 2, 3, 4, 5, 6, 7. Similar to the gap of 1, we have fixed our A's in place and we're rearranging the other letters. So that's 7 factorial. And again, similar to the gap of 1 there, we could shift our A's down the line so that we could have a scenario in which we've got the A and then 2 letters there, and then the remaining letters, this is 5, so 1, 2, 3, 4. And then we keep pushing these A's down the line, but still maintaining our gap of 2. So how many scenarios are those going to be? This here is our first scenario. So that's 2, that's 3, that's 4, that's 5, that's 6. So you multiply by 6. And so 7 factorial by 6 gives us 30,240. So let's tally up our 3 possibilities. Our total is going to be, that's 40,320, that's 35,280, plus the last one, that's 30,240. So if we punch this into the calculator, that's 40,320 plus 35,280 plus 30,240. That gives us 105,840, and that's our final answer. Number 3, a fair coin and an ordinary fair 6-sided dice are thrown at the same time. Random variable x is defined as follows. If the coin shows a tail, x is twice the score on the dice. If the coin shows a head, x is the score on the dice. If the score is even and x is 0 otherwise. Let's go through all the possible scenarios. So let's start with the one where the coin shows a tail. So if it shows a tail, x is twice the score on the die. Die score, die is 1. This leads us to a score of 2. And if die is 2, this leads us to a score of 4. If the die shows a 3, this leads us to a score of 6. If the die shows a 4, this leads us to a score of 8. If the die shows a 5, we get a score of 10. And finally, if the die shows a 6, we get a score of 12. All right. And now let's evaluate the scenarios for head. So if the coin shows heads and the die is 1, what score do we get? They said if it shows a head, X is the score in the dice. If the score is even, it's 0. Otherwise, 1 is not even. So this gives us a 0. And then if we've got a 2, 2 is even. So it's the score on the die, which is 2. And then we go on to 3. 3 is not even. So we get 0. 4 is even. So it's 4. And then 5. 5 is not even. So we get a 0. And then finally 6. 6 is even. So we get a 6. Right? So what are the possible values that this random variable can take? We've got 0, we've got 2, we've got 4, we've got 6, we've got 8, we've got 10, and we've got 12. All right. So let's draw up our probability distribution table. That's going to be x, and then the probability of x is equal to x. So we said the values that our random variable can take are as follows: 0, 2, 4, 6, 8, 10, and then 12. Okay, what is the probability of getting a 0? Remember, we've got a total of 12 outcomes because from the tails here, we've got 6. And from the heads, we also have 6. So that's a total of 12. So how many zeros did we obtain from 12 over 10 squared? 1, 2, 3 zeros. So 3 zeros. And then twos, we've got a 2 here. So 1 and 2. So 2 out of 12. And then fours, we've got 1, 2. So it's also 2 out of 12. Sixes, we've got 1, 2. That's also 2 out of 12. Eights, we've got 1. So 1 out of 12. 10, we've got 1, 1 out of 12. And then 12, we've got 1, 1 out of 12. Let's check that our probabilities add up to 1. 3 plus 2 is 5, plus 2 is 7, plus 2 is 9, 10, 11, 12. 12 over 12 is 1. So that's fine. Let's close up the cells of our table. So this is going to be our probability distribution table. All right. Make sure you use a ruler to draw your table. Part B says find var of x. So the formula for var of x is equal to, as the summation of x squared p minus the expectation of x squared. So we need to start off by finding our expectation of x, which we can find using the summation of xp. So this means the expectation of x is going to be equal to, you're just multiplying this value here by this value, then you add. So 0 times 3 over 12, I won't include that because if you multiply by 0, you get 0. Then you go on to the next one, 2 times 2 over 12 plus 4 times 2 over 12 plus 6 times 2 over 12 plus 8 times 1 over 12 plus 10 times 1 over 12 plus 12 times 1 over 12. Okay, so the expectation of x is equal to, let's punch this into the calculator, that's 2 times 2 over 12 plus 4 times 2 over 12 plus 6 times 2 over 12 plus 8 times 1 over 12 plus 10 times 1 over 12 plus 12 times 1 over 12, and this gives us 9 over 2. So our expectation of x is 9 over 2. Now we need to find the summation of x squared p. So it's essentially this expression, except now every x value is squared. So it's going to be 2 squared times 2 over 12 plus 4 squared times 2 over 12 plus 6 squared times 2 over 12 plus 8 squared times 1 over 12 plus 10 squared times 1 over 12 plus 12 squared times 1 over 12. Okay, so the summation of x squared p is equal to, let's punch that into the calculator, 2 squared times 2 over 12 plus 4 squared times 2 over 12 plus 6 squared times 2 over 12 plus 8 squared times 1 over 12 plus 10 squared times 1 over 12 plus 12 squared times 1 over 12, and this gives us a 35. So it means our variance of x is going to be equal to 35 minus our expectation squared. So minus 9 over 2 squared. So var of x is equal to, let's punch this into the calculator, that's 35 minus 9 over 2 squared, and that gives us 59 over 4 or 14.75, and that is our final answer. Number 4, the heights in meters of white pine trees are normally distributed with mean 19.8 and standard deviation 2.4. In a certain forest, there are 450 white pine trees. Part A, how many of these trees would you expect to have height less than 18.2 meters? Alright, so let's define our random variable. We're saying h is going to be the heights in meters of white pine trees. Okay, so I'll just status distribution, since h is pretty obvious that I'm referring to heights. This is normally distributed with mean 19.8 and standard deviation 2.4, so variance is 2.4 squared. All right, and in a certain forest of 450 white pine trees, how many of these trees would you expect? Okay, so let's find the probability of one of these trees having a height less than 18.2. So let's standardize. That's going to be z is less than 18.2 minus 19.8, and this is over our standard deviation 2.4. So that's the probability that z is less than, let's punch that into the calculator, 18.2 minus 19.8 over 2.4, and this gives us negative 0.667, and so this is essentially 1 minus 5 of 0.667. We need to read off the value of phi of 0.667 from the normal distribution tables. So that's 0.7477, and this gives us, that's 1 minus 0.7477, that gives us 0.2523. So our final answer, or not final answer actually, so this is the probability of one tree having a height less than 18.2 meters. What about 450 trees? So multiply by 450, we'd expect 113.535 of them to have a height less than 18.2 meters. So let's round that up to 114 trees. The heights in meters of red pine trees are normally distributed with mean 23.4 and standard deviation r. It is known that 26% of red pine trees have height greater than 25.5 meters. Okay, so I'm going to say that r follows a normal distribution with mean 23.4, and sigma we do not know, that's what we want to find. Okay, it is known that 26% of red pine trees have height, so the probability that r height is greater, so r is greater than 25.5, 25.5 is equal to 26%, so 0.26. So let's standardize. This would be said is greater than 25.5 minus our mu, which is 23.4, over our standard deviation sigma, This is equal to 0.26. And so this is the probability that Z is greater than 25.5 minus 23.4, that would be 2.1. So 2.1 over sigma, and this is equal to 0.26. I'm just going to rewrite this as Z. So probability that Z is greater than Z is equal to 0.26. And let's sketch a bell curve for a problem. So we'd have 0 over here. And we're saying that the area to the right of Z is 26%. So that means Z is probably somewhere here, such that this area to the right of it is equal to 26% or 0.26. And so this means the area to the left is 1 minus 0.26, which is 0.74. So if we want to find this Z value, is going to be arc-phi of 0.74. All right. So let's read off the Z value that corresponds to a probability of 0.74 from our normal distribution tables. So you get 0.643. That is our Z value. Now you notice that essentially this Z value is just a placeholder for 2.1 over sigma. So in other words, Z is equal to 2.1 over sigma. And so that means 0.643 is equal to 2.1 over sigma. So we can say that sigma is equal to 2.1 over 0.643, which means that sigma is equal to, let's punch that into the calculator, 2.1 over 0.643, that's 3.27, correct to three significant figures, and that's our final answer. Number 5. In a class of 21 students, there are 10 violinists, 6 guitarists, and 5 pianists. A group of 7 is to be chosen from these 21 students. The group will consist of 4 violinists, 2 guitarists, and 1 pianist. Part A. In how many ways can the group of 7 be chosen? Alright, so we want to pick 4 violinists from 10. So that's 10 choose 4. Multiplied by, we want to pick 2 guitarists from 6, so 6 choose 2, and we want to pick 1 pianist from 5, so that's 5 choose 1. Okay, so let's simplify this. This is 10 choose 4 multiplied by 6 choose 2 multiplied by 5 choose 1. This gives us 15,750. On another occasion, a group of 5 will be chosen from 21 students. The group must contain at least 2 violinists, at least 1 guitarist, and at most 1 pianist. Okay, part B, in how many ways can the group of 5 be chosen? Alright, so let's write down all the possible scenarios. So we can pick 2 violinists and have at least 1 guitarist, so 1 guitarist. Okay, so this scenario will not work because we can only have at most 1 pianist unless there was another group that was mentioned. No. So we can have at most 1 pianist, and if I put 1 pianist here, we end up selecting 4 but want to pick a total of 5. So I can't have that scenario. So I'm going to go to 2 guitarists, which allows us to pick 1 pianist. Okay. All right, so we could also have 2 violinists, and we could have 3 guitarists and 0 pianists, because we're not forced to pick a pianist. We can have 0 pianists. Or we could have 3 violinists and then have 1 guitarist and have 1 pianist. And we could also have 3 violinists, 2 guitarists, and 0 pianists. Okay, and then finally we can have 4 violinists, 1 guitarist, and 0 pianist. These are all the possible scenarios that satisfy the conditions they have given us. So let's start by evaluating the first one. We're going to be picking 2 violinists from how many violinists? From 10. So it's going to be 10 choose 2 multiplied by, we're picking 2 guitarists from 6. So 6 choose 2 multiplied by, we're picking one pianist from 5, so 5 choose 1. All right, so let's evaluate that. That's 10 choose 2 multiplied by 6 choose 2 multiplied by 5 choose 1, and that gives us 3,375. Let's go on to the next scenario. Again, we're picking 2 violinists from 10, and now we're picking 3 guitarists from 6, so 6 choose 3, and then 0 pianists from 5, so 5 choose 0. This is equal to 10 choose 2 times 6 choose 3 times 5 choose 0. That's 900. And then the next scenario, we are picking 3 violinists from 10, so 10 choose 3 multiplied by 1 guitarist from 6, so 6 choose 1 multiplied by 1 pianist from 5, so 5 choose 1. So this is 10 choose 3 multiplied by 6 choose 1 multiplied by 5 choose 1, which is 3,600. And then now again it's still 10 choose 3 for the violinist. Then we're picking 2 guitarists from 6 and 0 pianists from 5. So that's 10 choose 3 times 6 choose 2 times 5 choose 0. And that gives us 1,800. And then here we are picking 4 violinists from 10 multiplied by, we want 1 guitarist from 6 multiplied by, we want 0 pianists from 5, so 5 choose 0. Okay, so that's 10 choose 4 times 6 choose 1 times 5 choose 0, which is 1,260. Let's tally up all the results from our 5 different scenarios. So total is equal to, that's 3,375 plus 900 plus 3,600 plus 1,800 plus 1,260. So that means therefore the total is equal to, that's 3,375 plus 900 plus 3,600 plus 1,800 plus 1,260. This gives us 10,935, and that is our final answer. Number 6. Teams of 15 runners took part in a charity run last Saturday. The times taken in minutes to complete the course by the runners from the Falcons and the runners from the Kites are shown in the table. Part A. Draw a back-to-back stem and leaf diagram to represent this information, with the Falcons on the left-hand side. Alright, so let's set up our stem and leaf diagram. Okay. And then we want our stem going right down the middle. Okay. And what's on which side? They want the Falcons on the left, so Falcons. And then on the right, who's going to be their Kite? And let's see what our data looks like. What's the smallest value in our data set? Okay, it's going to be in the 30s. All right, it's arranged in rank order, it seems. So our smallest value is 30. So I'm going to use a 3 here, and our largest value is 76. So 3, 4, 5, 6, 7. And I'm going to create a key at the bottom and say that if our data is of the form, you've got a 4 here, and you've got a 2 here, and a 3. This means 42, what's our unit? Minutes. 42 minutes for the Falcons. For the Falcons, let me extend this so that it doesn't look like 41. Okay. Okay. So that's 42 for the Falcons and 43 minutes for the Kites. 43 minutes for the Kites. Okay. Draw back-to-back stem. Let's plot our data. So we'll start with the Falcons. We've got 38 and 39. So 8, 9, got 2, 4, 6, 8, 2, 4, 6, 8. Then we've got 0, 1, 2, 0, 1, 2, 6, 8, 9, 6, 8, 9, and then 4, 9, 4, 9, and finally the 76. Okay, let's do the same for cards. So it starts at 32, then we've got 0, 0 on the 40s, 0, 0, 5, 7, 8. So 5, 7, 8. Then we go on to 2, 4, 8, 2, 4, 8, 9, 9, 9, 9. Then we've got 0, 1, 3, 5. 0, 1, 3, 5. Okay, so that is our back-to-back stem and leaf diagram for the falcons and the kites, including the key. The key is key, no pun intended, but it is required. You get a mark for including a key. Part B, find the median and interquartile range of the times for the falcons. So the median position is going to be at half n plus 1. Where n is our sample size, we are looking at 15 runners. So median position is going to be half times 15 plus 1, so that's half of 16. Median position is 8. So let's find the value in the 8th position for falcons. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that's 51 minutes. Our median is 51 minutes. So we can say median is 51 minutes. And then we also want our interquartile range. So interquartile range we get from saying upper quartile minus lower quartile. Okay. So to get our upper quartile position Q3 is going to be 3/4 of n plus 1. So our n we said is 15. So this is 3/4 of 16, which is going to be 4, 8, 12 is 12. So Q3 is in the 12th position. Instead of counting from the beginning, we know that our median is in the 8th position. So this becomes 9, 10, 11, 12. So 59 is Q3. So our interquartile range here is 59 minus our Q1. So Q1, the lower quartile, is going to be a quarter n plus 1. So quarter of 16, so Q1, the quarter of 16, which is just simply 4. Q1 is equal to 4. So in the 4th position, I'll use a different color. So 1, 2, 3, 4. It's 44. So Q1 is 44. So that's 59 minus 44. So interquartile range is going to be, that's 59 minus 44. That's 15 minutes. Okay. And that will be our final answer. Let X and Y denote the times and minutes of a runner from the falcons and a runner from the kites, respectively. It is given that the summation of X is equal to 792. The summation of X squared is 43,504. The summation of Y is 783. The summation of Y squared is 42,223. Part C, find the mean and standard deviation of the times taken by all 30 runners from the two teams. Okay, so this is combined mean and standard deviation of income. So to get our combined mean is going to be equal to the summation of all the times from the falcons, so the summation of X, plus the summation of all the times from the kites, so that's the summation of Y, and this is all over the total number of runners, which is 30. Okay, so our mean is equal to 792, that's our summation of X here, plus our summation of Y, 783, and this is over 30. So our mean is That's 792 plus 783 over 30. That gives us 52.5. And now we also need to find our standard deviation. So the formula for combined standard deviation is going to be the summation of x squared plus the summation of y squared over the total number of runners, which is 30, minus our mean squared, the combined mean that we got. So minus, I'll just write it as mean squared. Okay, so that sigma is equal to the square root of the summation of x squared is 43,504 plus the summation of y squared, that's 42,223 over the total number of runners minus our mean squared, 52.5 squared. So sigma is equal to, let's punch this into the calculator, that's the square root of, that's 43,504 plus 42,223 over 30 minus 52.5 squared, and this gives us 10.1 as our standard deviation. So that will be the final answer. Mean is 52.5, standard deviation or sigma is 10.1. Number 7, in a game, players attempt to score a goal by kicking a ball into a net. The probability that Leno scores a goal is 0.4 on any attempt, independently of all other attempts. The random variable x denotes the number of attempts that it takes Leno to score a goal. So here we're looking at the number of attempts until Leno scores a goal. So we're looking at the number of trials up until a first success. So this means that this is a geometric distribution. And our probability of success is 0.4. We want to find the probability that x is 5. So that's going to be equal to, that's going to be q. Our q is 1 minus p, so 1 minus 0.4, q is 0.6. It's q that's raised to the power of 4 multiplied by the probability of success, 0.4. So this should be the probability that x is 5 is equal to, let's punch this into the calculator, that's 0.6 to the 4 multiplied by 0.4, and this gives us 0.0518 to 3 significant figures. Part B, we want to find the probability that x is between 3 and 7 inclusive. That's a long calculation. So 3, so essentially we're going to want 3, 4, 5, 6, and 7. Okay, so 3 is going to be 0.6 to the power 2 times 0.4. Then 4 is going to be 0.6 to the 3 times 0.4. Then 5 is 0.6 to the 4 times 0.4. Then 6 is going to be 0.6 to the 5 times 0.4. And then finally 0.6 to the 6 times 0.4. Okay. So therefore, the probability of x being between 3 and 7 inclusive is equal to, let's punch this into the calculator, that's 0.6 squared times 0.4 plus 0.6 cubed times 0.4 plus 0.6 to the power 4 times 0.4 plus 0.6 to the 5 times 0.4 plus 0.6 to the 6 times 0.4, and this is equal to, that's 0.332, and that's our final answer. Part C says find the probability that Leno scores his second goal on or before his fifth attempt. Alright, so he can either score his second goal on the second attempt, or the third attempt, or the fourth attempt, or the fifth attempt. So let's start with he scores his goal on the second attempt. So that's going to be 0.4 times 0.4, because that means he scored his first goal on the first attempt and then his second goal on the second attempt. So that gives us that 0.4 squared, 0.16, right? 0.16, yes. And then he could also score his second goal on the third attempt. Okay. However, this means he either scores his first goal on the first attempt or the second attempt. So we have to multiply by 2. And this is going to be he's scoring 2 goals, so 0.4 squared. And he's going to miss one of the attempts, so times 0.6, which is 2 times 0.4 squared times 0.6. And that gives us 0.192. Or he could score his second goal on the fourth attempt. So that's 1, 2, 3, 4. Okay. And this means that his first goal is either on the first, second, or third attempt. So we multiply by 3. And we know that he's going to score 2 goals and miss 2. So 0.4 squared for the scored goals and 0.6 squared for the missed goals. So that's 3 times 0.4 squared times 0.6 squared, which gives us 0.1728. Or finally, he could score his second goal on his fifth attempt. So that's 1, 2, 3, 4, 5. He scores here. And this means he's either scoring his first goal on the first, second, third, or fourth attempt. So we multiply by 4. And then we know that he's going to score 2 goals, so 0.4 squared. And he is missing 3 goals, so that's 0.6 cubed. So that's 4 multiplied by 0.4 squared times 0.6 cubed, which gives us 0.13824. Let's add up all of these scenarios to get the total probability. That's 0.16 plus 0.192 plus 0.1728 plus 0.13824. And therefore the total is that's 0.16 plus 0.192 plus 0.1728 plus 0.13824. And this gives us 0.663, correct to 3 significant figures, and that's our final answer. Leno has 75 attempts to score a goal. Part D. Use a suitable approximation to find the probability that Leno scores more than 28 goals but fewer than 35 goals. So we've been told that Leno has 75 attempts to score a goal. So let's define our random variable L as number of goals scored by Leno. Goals scored by Leno. And this is a binomial distribution. And just a heads up, at AS level, you're only going to be doing a normal approximation to the binomial distribution. So pretty much anytime they ask you for a suitable approximation, it's going to be a normal approximation to the binomial distribution. All right, so L follows a binomial distribution, and our number of attempts, 75. Probability of scoring a goal is 0.4 from earlier. 0.4. So that's our probability of success. Okay. And you can just double check to make sure that the conditions for the approximation are satisfied. So the conditions should be that NP is greater than 5 and NQ greater than 5 as well. So we can check what is our NP. NP is 75 times 0.4. So NP is equal to, let's punch that into the calculator. 75 times 0.4, that gives us 30. Okay. So NP is equal to 30, which is greater than 5. And we can check NQ as well. NQ would be 75 times 0.6. So NQ is equal to 75 times 0.6. That's going to be 45. So NQ is equal to 45, which is greater than 5 as well. So we can use a normal approximation to the binomial distribution. So use normal approximation. And X, or in this case, we're using L. So L follows an approximate normal distribution with the mean being NP and the variance being NPQ. So this means L follows a normal distribution. The mean NP we already evaluated to be 30. NPQ, let's find that. As NPQ is 75 times 0.4 times 0.6. So NPQ is equal to, this is 75 times 0.4 times 0.6, and this gives us 18. So that's 18 over there. And we want to find the probability that, let's check, Leno scores more than 28 goals. So it's going to be greater than 28, but fewer than 35 goals, so less than 35. But I want you to remember that this question was defined under a discrete distribution in the binomial distribution, and we have approximated to a continuous distribution. So we have to apply continuity correction. So this part where we're saying L is greater than 28, what would that become? 28 represents any number from 27.5 all the way up to 28.5. And we're saying L is greater than 28. Okay, so this means we don't want to include 28. We're moving to the right, but we don't want to include 28. So we're taking numbers greater than 28.5. All right, so that's going to be L is greater than 28.5 after continuity correction. And then the other part, L is less than 35. So 35 represents all numbers from 34.5 all the way up to 35.5. And in this case, we're saying L is less than 35. So we don't want to include 35 and we're moving to the left. So we want to take less than 34.5 so that we ignore all numbers that are represented by 35. So less than 34.5. Okay. And now that we've done our continuity correction, we can standardize. So that's going to be 28.5 minus our mean, which is 30, divided by our standard deviation. So that's square root of 18. This is less than Z, which is less than 34.5, minus our mean, which is 30, over the square root of 18. And so let's simplify this. We've got 28.5 minus 30 over the square root of 18. And this gives us negative 0.354 is less than Z, which is less than. Then we've got 34.5 minus 30 over root 18. That gives us 1.061. Okay. So that there can be written as phi of 1.061 minus 1 minus phi of 0.354. Okay. So let's read off the values of phi of 1.061 and phi of 0.354 from our normal distribution tables. So this becomes 0.8556 minus 1 minus 0.6383. Okay, let's punch this into the calculator. This is 0.8556 minus 1 minus 0.6383, and this gives us that's 0.494, correct to 3 significant figures, and that is our final answer, and that's the paper as well. I hope you guys found this video useful, and if you did, please share it with someone who you think this might help, and also make sure to leave a like, subscribe, and comment down below which paper would you like to see me break down next. Otherwise, check out all the other videos on my channel, and I will see you next time. Bye bye.